Aqui na Unicamp a gente já está tudo pronto no gravando, na hora que você quiser começar, fica à vontade.
Tá. Então, posso começar então? Can I start? Okay. So, good afternoon, everybody. Today we're going to talk about a very important subject, the conversion of thermal energy. This is going to take 2 or 3 weeks for us to cover this subject, and we'll focus further on biomass, biogas, and solar thermal power plants. However, today I will be talking about the theoretical framework and also the historical context. I'm going to try to introduce this subject in association with its historical context. Okay, so why this is so important, why I said that this is a very important subject. You know that most of our electrical energy, the world electrical energy consumption, comes from thermal conversion. I mean conversion of thermal energy into electricity by some special methods, which we will elaborate further on. Okay, so I just put this reminder here: 80% of the world's electrical energy generation comes from thermal conversion. Various types of technologies for thermal conversion, which I will try to elaborate. Okay, to elaborate a little bit more on this subject, let's take this very recurrent figure. I'm going to be showing you this figure several times during this course. This is the U.S. energy use in 2013. Actually, this is a very interesting figure because first it's a Sankey diagram, so we have a very good idea of the sources and the destination, the uses of energy. Okay. And well, it's also representative of the world's consumption, the world average consumption, because you know the Brazilian grid, the Brazilian matrix, as we say here in Brazil, is kind of different. So that's why I use sometimes these kind of pictures. So you can see in a Sankey diagram, you have the energy sources: solar, nuclear, hydropower, wind, and so on. And on the right, you have the destinations, or the sectors that are consuming energy. You see the residential sector, commercial, industrial, and transportation. So when you look at electricity generation and when you look at the sources, first of all, you see that you have nuclear energy, which is also a thermal source. You have hydropower and so on, which is not a thermal source, okay? And the same thing you can track, for instance, the using in industry. You use a lot of natural gas in industry. So that's how you interpret this kind of graph. As far as electricity generation is regarded, you know, most of the conversion of thermal sources to electricity is done through a Rankine or a Brayton cycle. My intention is to explain what is a Rankine or a Brayton cycle. This is going to be done today, and we're going to do some calculations also. But if you look at the sources of electricity generation, the main sources, you see nuclear is a non-renewable source. It's in a strict sense, it's non-renewable, but you have supply for thousands of years. Okay, but you see, natural gas and coal are non-renewable sources, and they play a very important role in electricity generation. You also have hydropower, wind power, and a little bit of biomass here, which are renewable sources for electricity generation. If you look at the transportation sector, which is not electricity, but also uses thermal cycles like the Otto cycle, the diesel, or even the Brayton cycle, the major contribution comes from petroleum. So petroleum is essentially a fuel source for the transportation sector. You see a very small amount of electricity being used in the transportation sector, 0.02526, which is for electrical trains, for instance, like it is shown here. So you see that you have a lot of thermal conversion here. Also here, see what's not thermal conversion is electricity and possibly wind, but it's not significant. Okay, so Rankine, Brayton, Otto, diesel, and Brayton cycles are cycles of conversion of thermal energy to exergy, or organized form of energy. You can think of electricity. Moving further, and this is also important. You remember I said in the first class when I talked about the climate change and transition of the matrix grid. It would be interesting to be able to construct a negative carbon cycle because, you know, fossil sources like petroleum, coal, and gas will remain for a lot of time in the world scenario because of new technologies and so on. So it would also be very interesting if we develop a negative cycle in which you still can produce energy. Okay, so that's a slide from the first class, which I'm bringing it here to remind you the importance of thermal conversion. We need to produce energy, organized energy, exergy, and also we would like to inject CO2 in the underground in order to retain it, okay, in order to decrease the concentration of CO2 in the atmosphere. Okay, and that's so, I don't know if you remember this slide, by doing so you are able to collect CO2 from several producers, and this company will operate an inverse well, an inverted well, or an injection well. It's going to inject CO2 in the underground. Okay, so just to give you some informations and some references where to read, most of many things I'm saying I'm giving you in this course, not only in this class, comes from this very excellent book by Daniel Yergin, in which he describes the evolution of energy systems, technologies, regulation, and markets. So it's not a very scientific book, but it gives a lot of information about the story, how our energy systems evolved during the last 150 years, for instance. Okay. Well, let's start by stating what is actually the problem, what I call the problem of converting energy or a disorganized form of energy. Thermal energy is a disorganized form of energy. What is the problem of converting it into mechanical energy, which is a form of organized energy? And for that we give a special name. We give this name exergy. If you're not familiar with this term, there's no problem. You can simply think in electricity or kinetic energy. Electricity for appliances, for instance, for using appliances, and kinetic energy for the use in the transportation sector. Okay, so what is the problem when we try to engineer systems for this conversion? This question we're going to answer it today, and it is related to the second law of thermodynamics, which I will show you in a few slides. And it is also related to what we call the arrow of time. Okay, I mean, the fact that the time always moves forward is related to a certain limit of this conversion, for the efficiency of this conversion. Okay, that's in a few words a quick glance in what we're going to see further on. And I also want to show you a demonstration of a thermal conversion. I brought this small machine here. I don't know if you can see it. Actually, it's one of those. I'm going to go back some slides. It's a kind of one of those cycles, autodiesel Brighton. This is actually what we call a Stirling cycle. So this is a Stirling machine, and it's a machine for the conversion of thermal energy, which may be coming from the guy's hand here. Okay, so it takes the heat from the hand of the person holding the machine, the Stirling machine, and it converts this heat to kinetic energy. So I brought also some hot water from IT, and I'm going to show you how this works in a few seconds, because if I use the heat of my hand, it's going to take a little while for the machines to start to turn. So I'm going to leave it here for a while, and I'm going further, and then I'll stop to show you the machine working. But what's happening here, let me explain in a little more details. Heat is being converted, heat from the hand or from the bottle that I hope you can see it here. Let me see if the guys from YouTube manage to see that. Yeah, they will. Okay. So heat is being transformed into kinetic energy, and that's the subject of today's class. We're going to write down all the equations and so on. Okay. Let me see if it's already turning. Yeah. So you see that it's getting heat from the hot water, and it's not working yet, but it will in a few moments. I'm going to move a little bit further, and then I'll stop to show you the demonstration. Okay. So before going to the theoretical framework, I'm going to give you a perspective on what I call a historical context, starting by or focusing on the disruptive improvements in the use of energy. This is very important. The first disruptive use of energy was the control of fire for food cooking, especially for thermal processing the food that we ingest. I already mentioned that, but I want to give you a little bit more details, because actually what happened, the control of fire didn't happen suddenly. Actually, it is the result of incremental technological improvements, starting by the control. We learned how to transport from burned to unburned areas. I mean, to transport fire. That's something that we didn't know how to start a fire, so we had to collect this fire somewhere and to transport this chemical reaction to the place where we want to use it. Also, a next evolutionary step was we learned how to start the fire, and we also built hearths and other kinds of fire enclosures in order to render the use of fire more efficient. And also we learned how to maintain for a long period of time, maintain this chemical reaction for a long period time, sufficient for cooking grains, for instance. So this can be stated as our first disruptive use of energy, actually. The second important step was the use of, let's say, wind, or for water pumping, grain processing, for propulsion, already mentioned in the transportation sector. And if we leap to only 200 or 300 years from today, we see that during the Victorian era, we learned how to do this conversion of thermal energy, which is a very abundant and easy to get source of energy, to work. When I say work, I mean force times displacement, mechanical energy. Okay, so we learned how to do that during this period. We're going to see that in a little while. And after learning how to convert heat to work, we developed general purpose engines, also machines like mechanical looms, tractors, excavators, and so on. This evolution here actually revolutionized our society. Okay, the control of fire represented a revolution in our evolution. You know, I said in the first class that even our brain was configured differently because we had access to a lot more food. But these changes here during the Industrial Revolution actually completely revolutionized our society. I'm going to show you that in a few slides. Let me see if my machine is already working. Okay, you see that it's turning. So I don't know if you hear the sound, but it's taking energy from the hot water. So there's a flow of energy. It's collecting energy from the bottom. Somehow this heat is being converted to a mechanical movement that you can see. The wheel is turning. And also a very important aspect of this conversion is that some finite amount of heat must be rejected to the environment. So this heat rejection is occurring on the top of the machine, where I'm with my finger with. Okay, so we're going to write down all the equations and see if it is possible or not to avoid rejecting heat, because you know, if you reject heat to the environment, this amount of energy is not being converted to mechanical energy. So ideally, it would be interesting not to reject zero energy to the environment. Okay, I'm going to show you that this is not possible. If you ask me because or why, I would say because time always flows forward. I'm not going to be able to elaborate on that, but the reasons are closely related. Okay, so I'm going to leave the machine just here. It will be turning during my talk. Okay, so coming back to our slides and moving on, these changes here resulted in what we call Industrial Revolution, which we can say started one of the aspects of the Industrial Revolution that I want to focus on, thermal energy conversion. We could say that it started in the United Kingdom, in the coal mines of the United Kingdom. Now you see it here. The problem in these mines was that you start digging deeper and deeper, as you can see here. I don't know if you can see. As you started to dig deeper and deeper to get coal, what happened is that you have water that started to seep and accumulate in these galleries. So you have to have some kind of system to drain this water from the underground in order to enable for the miners to work and to get the coal. Okay, so in the beginning, this water drainage was done by animals or even by humans, but as these mines started to grow, you animals or man didn't have enough power in order to remove the amount of water that was increasing and increasing. Okay, so the first thermal machines were developed. As you can see here, we're going to see the machine, a cable, and which goes down to the mine. Okay, and you see the coal here being fed to the thermal machine. The first of, let's say, the first of these machines was Thomas Savery's machine. The important point is the date, in 1698. Actually, it was a very strange machine and a very inefficient machine, but it was better than having, let's say, 100 horses side by side trying to pull all the water that was seeping into the mine. Actually, this machine by Thomas Savery is a vacuum machine, so it's different from this machine that I'm showing you here, and it used the vacuum produced in different chambers. So this chamber here, you produce vacuum, and this low pressure actually sucks the water from the bottom of the mine. We can see this effect also in Thomas Newcomen machine, which is a little bit better than Thomas Savery's machine. We have an animation here on the right. I'm not going to bother you with these details now. We're going to see it in very much details in a few moments. But you see that there's some point in the cycle in which this pink steam, the steam is represented in pink. So I don't know if you can see, but there's a specific moment in which you inject liquid water, and this liquid water promotes the condensation of this steam. So this condensation creates a vacuum, actually a low pressure inside the piston, and the atmospheric pressure actually pushes the piston down. So these machines, Thomas Savery's and Newcomen's, are called atmospheric machines. The effect that I'm showing you here can be seen in this small movie. We can reproduce this at home. You see, you have a can, you put some water, then you heat in order to produce steam inside the can, and also to eliminate the amount of air inside. When you cool that, you see that steam condenses inside the bottle, and the atmospheric pressure crushes the can. Okay, we can see that in slow motion. So that's the same effect that these first machines used. You can do that at your homes. It's very easy. Okay, very easy to do. You don't need to use ice as it's shown here. You can use simply water from the tap. It's enough for the condensation of the steam inside the can. Okay. Next, a very important evolution was obtained by James Watt in 1763. And what he did was to separate the condenser, and this increased very, very much the efficiency of the conversion of energy. Let me go back some slides. The problem with Savery's and also Newcomen's machine was that the consumption of heat and the consumption of coal was very, very significant for a given amount of work produced. So that was a problem, a very big problem actually, and it was solved by James Watt by building a very efficient machine. And for that, he simply separated the condenser from the piston. Let me just cancel. Okay. Okay. So moving further, when Watt managed to develop a very efficient machine, what this caused was the development of general purpose engines, like this one in the picture here. In this, by general purpose, I mean engines suitable for the application in the transportation sector and so on and so forth. And this actually represented a very, very important revolution. First, in the transportation sector, you can imagine the effect, the revolutionizing effect that a tractor represents for agriculture, for instance. You can do the calculations. What is the amount of work that a horse can produce by pulling a plow, for instance, for plowing the soil? You can multiply that by 10, by 50. That's the capacity of a steam tractor. So this represented actually a very important increase in food production. Actually, the historians say that Thomas Malthus' bomb actually was disarmed by the invention of the steam tractor. Also, navigation. You know that before the use of steam, you have to rely on wind power for the propulsion of boats. So you need wind to go from A to B. You always need wind. When you have steam, if you have steam, you don't need wind. You need some fuel, wood or coal, and that's okay. You have a lot of coal, but also a lot of wood, and you also could navigate through rivers. Okay, I don't know, somebody's trying to call me here. Okay, so also this represented a very important revolution, especially in the exchange of goods. You can think about, for instance, the impact that this represented in the United States, for instance. You know, cattle was raised in the interior near Texas and Oklahoma, and the most important markets were in New York and Los Angeles, for instance. So with the use of boats, you managed to transport this meat to the sea through the Mississippi River and then to New York, for instance. So this represented a very important revolution in commerce, and also in terms of health. Okay, you can you figure the impact that a steam excavator had in the cities? Because with steam excavators, you were able to build canals and for draining sewage, and this represented a very positive impact in people's health. Also, the use of steam excavators enabled the construction, as you see here, of the Suez Canal in 1869. And with the Suez Canal, you know, you don't have anymore to go from United Kingdom to India, for instance. You don't have to go all the way down to South Africa and then to India. You just you shorten your trip in, I don't know, 6 months or 1 year. I don't know. I'm inventing numbers, actually. Okay, and not only the Suez Canal, but also the Panama Canal in 1881. And you see the picture here of a steam excavator. These constructions, the Suez Canal and the Panama Canal, represented major engineering feats, actually, at a time, and it wasn't possible without this kind of machine. The Suez Canal, the story of the Suez Canal is a very interesting. If you have the opportunity of watching a documentary or something like that, it's a very, very interesting um, thing to see, the construction of the Panama Canal, because it's closely related to actually to politics. You see here, actually the country called Panama was created because Colombia didn't agree with the United States, they didn't want to let the United States build the Panama Canal. Okay, so there's interesting stories about that, and also related to the plague, actually, to yellow fever. You see that a very, very important problem, which the French, because the French constructed the Suez Canal, they tried to construct the Panama Canal, and they didn't they didn't succeed because of yellow fever. And then when the United States bought the concession to build the Panama Canal, the first thing they did was try to eradicate the yellow fever. And this was done by Theodore Roosevelt, the president here. And if you don't remember him, I'm sure you remember the movie. What's the name? A Night at the Museum or something like that. And this character here actually was President Roosevelt, a very, very interesting character. Okay. But also the use of steam, the possibility of converting thermal energy to mechanical energy, enable the development of machine tools or mechanical looms, as it's shown here. You see you have the mechanical energy coming in this X here, which is transferred to the looms through these rubber belts or tissue belts. Okay, and the story of the loom actually is very interesting because it leads to the development of the computer. It's very surprising, but the development of the computer is related to the mechanical loom. And that started with Jacquard, a French guy who developed the programmable loom. So he coded the drawings that you want to put on the tissue were programmed in wood cards, punched wood cards, like the first computer's first punch cards. And this technology actually, well, the programmable loom is a machine that you can, if you change the program, the set of cards here, you change the figure that's going to be drawn here, okay? And that's exactly what the computer does, okay? So the development of the mechanical and programmable loom led to the development of the computer, okay? But let's try to generalize a little bit what we have said already. Remember, I'm talking about the disruptive improvements in the use of energy. So I'm talking about exergy, which we can think as mechanical work or electricity or kinetic energy, for large-scale production of goods, food, clothing, utensils, etc., and for broadening the access to services such as transportation, illumination, heating, etc. Okay, so what do you think this represents in terms of social changes? You know, this is possible only because you have this kind of thermal machine, machine that is capable of converting thermal energy to mechanical work. Okay, so this represented, this led to what we call the Industrial Revolution, which led to a better quality of life. Okay, and by better quality of life, I mean in an objective sense, because this can be measured through longevity, education, and income. So all these, let me see. So all these consequences led to higher longevity, better education, and increase in people's income. So you can quantify that through the HDA index. Okay. Um, Another reference that I want to give you is this book, a very interesting book, very, very interesting. I really recommend. Both books are very good. I really recommend them. But this one describes the history of the evolution of the steam technology and the corresponding social consequences, because they are very closely related. This is a very, I really would recommend you to read these books if you're interested in these subjects, okay? But we're talking about energy, we're talking about its social impacts, we're talking about how to convert different types of energy. But, you know, what is energy? That's a very interesting question. If you look in books and even good references, you often find this kind of definition. Is the capacity to do work, and by work we mean force times displacement, or torque times rotation, okay? So this definition actually represents a problem, because work also is energy, okay? It's mechanical energy. So it's like saying that energy is energy. So this actually does not answer our question. So I want to discuss a little bit this subject. And another reference, during this class, you know, I'm going to be using some concepts which are elaborated in this course of thermodynamics, and particularly the calculations that we're going to do, and also the concepts are in these two classes: Introduction to the First Law of Thermodynamics and Thermodynamic Properties and State Diagrams. They are in Portuguese. I don't have in English these videos, but if you're interested, this is a complete course on thermodynamics, which is entirely in video. You can use this reference if you want. Okay, but today's subject is covered in this class and also in this third class here. Okay. So when we try to figure out what is energy, we can first we recognize that there are different types of energy. Okay, I already mentioned we have organized types of energy, disorganized types of energy, but we also can ask ourselves, for instance, okay, I know that heat is a kind of disorganized energy, but what is heat? You know, in the past, people assumed that heat was a self-repellent fluid called caloric. No? So that's the origin of the word calor in Portuguese. It comes from the Latin caloric, which was this kind of fluid, this magic fluid which self-repels itself and was associated with heat. Another important question is, what is mechanical work? What is mechanical energy in terms of force times displacement? Another significant question is it possible to convert different types of energy, heat to work, work to heat, and so on? Are there efficiency limits to these conversions? Can I convert heat to energy with 100% efficiency and convert work to heat with 100% efficiency? You're going to see that this is not always the case. Also, different types of energy can perform equivalent amounts of work. So all these questions were in the heads of the researchers of the time, and I'm going to try to put ourselves in their shoes and try to reason as they reasoned back in the past. Okay, so but here and now we can state what I call working definition of energy, like this: energy is an abstract quantity with which we can express quantitative laws governing natural physical phenomena. For instance, the law of conservation of energy. Okay, any transformation is ruled by the conservation of energy law. Okay, the law of conservation of energy, and we can do calculations with that. So this definition, the most important word here is abstract. By abstract, I mean that energy actually does not exist. Okay, it's an abstract concept. It's like saying that energy is like the number one. The number one does not exist. It's an invention, an abstract invention, which we can use to count things, the number of birds in a tree, for instance, and make calculations. And so energy is exactly the same thing. It's an abstract concept, and we can use this concept to express quantitatively physical laws. And the physical laws, they exist. So it's a way of expressing quantitatively these physical laws. Okay? So in this moment, we are most concerned with this relation, the relation between transformation and energy. Why is that? Because, as I mentioned, we manage during time, during our evolution as a human species, we manage to control the use of energy for practical applications, and these applications involved transformation. For instance, transforming raw grains of bean into more digestible grains of bean. For that, we need heat. We need to thermoprocess these grains. Okay. Another type of transformation is to transform a metal sheet into, I don't know, an appliance, for instance, like pans for cooking. So in order to conform the metal sheet into the form of a pan, we need energy. We need actually mechanical energy. So to do any kind of transformation, actually, we need energy. So, and that's why, since we managed to control very, very huge amounts of energy, we managed to make very, very huge transformations. Okay, and this is done in nature in most many kinds of applications. A leaf, for instance, do exactly this. It captures the energy of the sun, transforms that into biomass, for instance, and well, you also have some consequences, let's say like that. Okay, so it's a transformation. Light is energy associated with light is transformed in energy associated in biomass. Okay, also cells fermenting can do that. Okay, let me go quick here. We do that in our bodies. Right? We take chemical energy and we transform in available energy for moving our muscles and for respiration and so on. And we also lose thermal energy here. And this is exactly what an internal combustion engine do. So it's a very similar combustion reaction, actually. You take chemical energy from your fuel, you transform that, this chemical energy, to mechanical energy in the X here. Okay, it's going to be transformed into kinetic energy, but you also lose thermal energy. We're going to see that it is impossible not to lose some amount of thermal energy, because we know that energy must be conserved, so the ideal scenario would be to convert 100% of this chemical energy to mechanical energy without losing any kind of energy. Okay, this would be a 100% efficient conversion, but I'm going to show you that this is impossible. Okay, and the first person that tried to study that was Joule. I'm sure you are aware of this, what they call the mechanical equivalent of heat. Heat, by heat I mean thermal energy. Actually, Joule constructed this machine, And by allowing this weight to decrease its height, it pulls the rope here, it turns the blade, the agitator inside the calorimeter, and by supplying a certain amount of mechanical energy, gravitational energy, this resulted in an increase in temperatures. So consequently, in an increase of thermal energy of the water surrounding the blades here. So in this experiment, work is totally converted to heat, to thermal energy. So and the equivalent calculated by Joule is given here. Okay, the important question is, how can we do the transformation in the opposite sense? Of course, this type of machine is not going to work, but we can always build something like this. And the idea and the question is it possible to convert 100% of heat to mechanical work? Okay, so let's see how it's in more details how it is done in Newcomen's machine. Let's see the specific cycles in order to try to answer this question, if it's possible to convert 100% of heat to work. Okay. The first step, I'm not able to stop the cycle here, but you see the first step, the beginning of the cycle, starts with the injection of steam at high temperature and pressure into the piston. So you have a boiler down here. You see the pink fluid is steam. When the valve here opens, the steam goes inside the piston. So that's step one of the cycle. Step two consists in promoting steam condensation by means of cool water injection, which creates a partial vacuum in the piston. I showed you that in a soda can. Okay, so this step two, the injection of cold water is done by this valve here. So you see when it opens, you see a squirt of liquid water inside the piston. And this liquid water, cold liquid water mixed with hot steam, promotes the condensation of steam. So you have partial vacuum inside, and the atmospheric pressure pushes the piston down, which pulls the bucket of water at the bottom of the mine. Okay, and step three, I already explained, through the action of atmospheric pressure, the piston is contracted, which pulls the rod down. Okay, and step four, the cycle is restarted. Okay, the problem at the time was that only a fraction of the heat is converted to work. Is it possible to develop a perpetual motion machine? I'm going to show you that if it was possible to convert 100% of heat to mechanical work, it would be possible to construct a perpetual motion machine. And this actually is related to the second law of the thermodynamics. Okay, you know, just as a reminder, the first law of thermodynamics is related to energy conservation, and the second law is related with this efficiency, the efficiency of the conversion of heat to work. We're going to see that in a few moments. So a very important person on all this development was Nikola Tesla, which was a French military cadet, and well, actually he asked himself the right questions, and he obtained very, very significant and important and consequential answers. First, he recognized that heat is a form of disorganized energy. It's inverted here. Okay, so heat is a form of disorganized energy. He also recognized that work is a form of organized energy. Sorry for the inversion. Okay, and this is the important part of Carnot's work. He demonstrated that work can be 100% converted to heat, but he showed that heat can be partially converted to work. This is astonishing and, let's say, surprising at the same time. I'm going to show you that. This is Carnot's work. It's the title is very interesting. Réflexion sur la puissance motrice du feu. Reflections or thoughts about the motive power of fire. Okay. We're going to come back in a few moments in Carnot's thoughts. But actually, it's a very sophisticated and elaborate thought. And it starts by recognizing different forms of energy. You have macroscopic forms and macroscopic and microscopic forms, okay, associated with a system. By system, let's think in terms of a bunch of particles moving around and confined by a box, like it is shown here. Okay, so these particles, they have individual velocities, but the resulting center of mass also may have a velocity. Okay, or what we call macroscopic velocity. Okay, so the macroscopic forms of energy, is associated with the system center of mass relative to an inertial referential. So it's the well-known kinetic energy. Sorry, it's half Portuguese, half English here. So we have kinetic energy and also potential energy. So V stands for the velocity of the center of mass, and Z is the height of the center of mass. So these are actually organized forms of energy. The microscopic forms of energy are actually associated with the individual motion of the particles that constitute the system. Okay, so you have molecular translation. This is closely related to temperature. You also have rotation, you have vibration, chemical energy, nuclear energy. If you want to produce energy by a chemical reaction, you break these liaisons here, okay, and you may have energy. If you break down the nucleus of these particles, you can have nuclear energy. Okay, so these types of energies are also associated with what we call energy models. Like kinetic energy is associated with wind energy, potential energy to hydroelectric power. Okay, so temperature, like geothermal or solar thermal. Chemical energy is a thermal power, general thermal power plant, which burns some fuel in order to obtain heat, and nuclear power plants. Okay, so Carnot started by recognizing these, and well, he asked himself if it's possible to build a perpetuum mobile. Okay, like in this picture here. Okay, so this leads to the first law of thermodynamics, and before that, the second law of thermodynamics, which I'm going to show you. Okay, so the first law of thermodynamics is actually an energy conservation principle, which is actually what we call an inventory, an energy inventory. Okay, like exactly the same thing that we do with our transaction account in our banks. So what is the law? The variation of the account balance is equal to the net income minus the net expenses. So we add all incomes, like salary or the incomes from a financial investment that we did. We subtract all our expenses, or expenses in the supermarket, the electricity bill, and so on and so on. And the difference is the variation of our account balance. Okay, energy is exactly the same thing. We're going to add all energy inputs, we're going to subtract all energy outputs, and the difference is going to be the variation of the energy balance within the system. Well, that's exactly what the first law says. Okay, so the first law of thermodynamics for open system, I'm going to state this law because we're going to use at the end of the class in order to analyze some systems. Okay, so we're going to develop some working equations which we're going to use at the end of this class and also in other classes in the future. Okay, so I need first to introduce a kind of a formalism based on which we're going to write down our equations. Okay, so by system, I already said it's a defined amount of mass surrounded by a boundary. Okay, surrounded by a boundary. This boundary can be it does not need to exist. It can be a virtual or imaginary or mathematical surface enclosing an amount of mass and separating this amount of mass from the surroundings. So it's like the rocket here. You see, we can put this imaginary surface here. Okay, so this is our imaginary surface. Our system is the rocket. I mean the fuel. You know, from the bottom to here, all this is fuel, energy, storage, and this is the payload. Okay, so this is a system, and one important aspect of this particular system is that you have mass flow through the boundary down here. Okay, so this is what we call open system. Okay, so just to be clear, an open system is a system in which you have mass flow through the boundary. Okay, so that's the definition of an open system. And we're going to do our banking balances on this system, this open system. Okay, so there's our system. That's the imaginary. Let me get my pointer. Okay, this cloudy form here is the imaginary surface that defines the boundary of the system. You see that you have energy flows through the boundary in the form of heat and work. Energy entering, energy exiting the system, but you also have mass flows through the boundary of the system. Okay, and well, with this flow, entering flow, and with this exiting flow, you have energy being carried inside and carried out of the system. Okay, associated with thermal energy and also what we call flow work. Why is that? Let me give you an example. You can suppose that you have a pool, okay, and you have hot water, a heated pool. You have hot water entering here. So even though the pool, the temperature of the pool, let's say 25 degrees, you may have hot water entering at 60 degrees here. Okay, so this water comes with a high amount of thermal energy, which will be dispersed, which will be used to heat all the water that is confined in the pool. Okay, so that's how thermal energy is associated with this input mass flow. And also, I don't know if my next slide states that, but what we call flow work is actually because, you know, the pressure inside the system may be different from the pressure outside of the system. So you may need to exert a force in order for this mass to enter the system. So this force, in order to equalize the pressure, is the associated with what we call flow work. Okay, so thermal energy transport associated with mass flow is actually the thermal energy or internal energy of the substance associated with mass flow entering or leaving the control volume that must be accounted for in our balances. Okay, and flow work is the mechanical work, force times displacement, necessary for an element of mass to be pushed into or pulled out of the system CV. The CV stands for control volume. Okay, so these are amounts of energy that we need to account for in our calculations. And as I said, the law of conservation of energy in the absence of nuclear reaction, okay, is that the total energy entering the control volume equals the rate of change of the internal energy confined in the control volume. If you have steady state, the system is not changing during time. This means that there is no net variation in the system's internal energy, zero here, okay? And this means that the total energy is entering the control volume is zero. This means that the energy that enters is equal the energy that exits the system. In mathematical terms, this can be expressed as it's shown here. Okay, so theta represents thermal energy, H is enthalpy, okay, which is a kind of internal energy. Actually, let me just write down you an equation here. The definition of enthalpy. Enthalpy, by definition, is a kind of energy, okay? So, by definition, it's equals to the internal energy, and this is actually it is temperature, plus pressure times volume, okay? And this quantity here is associated with flow work, okay? So enthalpy is a useful definition of energy which combines the internal energy of the substance associated with the translational movement of the particles of the system, okay, and also to the force necessary to push this element of mass inside the system, okay. So theta stands for internal energy, or what we call thermodynamic energy, but also with gravitational and kinetic energy, amounts of energy associated with this mass flow here, okay? Okay, so when we do this calculation, the first law of thermodynamics, you have heat entering the control volume, okay, here. You have work entering the control volume. You have heat going out and work going out here. So QE stands for entering, WE stands for entering, okay, and QS stands for, this is Portuguese actually, for the amount of heat that's going out of the control volume, okay. And this summations here stands for the energy associated with, I don't know, in the kth input flow, okay. So we're going to account because, well, I only draw one entering mass flow, but you can have several entering mass flows, okay. So if we combine terms here, for instance, I want to define the net heat input. So I combine what's entering and subtract what's exiting, okay. I want to calculate, to define the net work going out of the volume, okay. So I combine like this, and this is the net output energy associated with the mass flow. So combining these equations, okay, you have this form of the first law of thermodynamics, okay. We're going to use that in a few moments. Don't worry if you're not used to this law. It's only, I'm going back some slides, it's only an inventory, okay. It's a mathematical formulation of this kind of inventory, okay. So don't bother with mathematical representation of the first law. yeah, and just writing down according to the definition that we have made here, okay? So we're going to try to apply that in the thermal machines. In an important aspect to observe here is that our thermal machines have evolved a lot since the first ones in the 1700s to today. So how these very inefficient machines evolved to these very, very efficient machines, which today, as I said, represent or responsible for 80% of all electrical energy generated in the world. Okay, a typical power plant. We're going to, I don't know if you understood what I'm trying to say. We're going to apply these equations, the first and the second law of thermodynamics, to a thermal power plant, okay, in this class. And next week we're going to see in more details a biogas thermal power plant and also a biomass thermal power plant. Okay, so in this class I'm simply talking about general power plants like this one in Turkey. Okay, actually it uses coal as fuel. Okay, so when you see a power plant like this, a thermal power plant, you need to always look for the energy source, for the fuel. In this case, it's coal. Okay, and well, you can see several other characteristic aspects of a thermal power plant. You see, for instance, well, as I said, the heat supply to the power plant obtained from burning coal. You also see, as I said, it's impossible not to reject some amount of heat. Okay, so you always see a system of heat rejection. So in this case, I'm not sure, it seems to be cooling towers. Okay, and you also see connection to the electricity grid or some kind of output of the mechanical exergy or electricity. Okay, the what we call the surplus exergy. Okay, the remaining organized form of energy that we can sell to somebody, or we can transform that to kinetic energy in our cars, for instance. Okay, so this is very typical in all thermal power plants. As I said, heat supply, heat rejection, and the surplus output. Okay, the important question is, I'm going back one slide. Okay, because let's say I want to sell electricity. So in terms of business, I want to produce this electricity by burning the minimum amount of coal possible. I want to convert 100% of this heat to electricity. Or if I already know that this is impossible, I want to convert the maximum amount of heat to exergy, to surplus exergy, which means that I want to minimize the rejection of heat. Okay, so the important question is there a physical limit to the efficiency of the conversion of heat to mechanical work? Is there a limit to the conversion of organized, let me start again. Is there a physical limit to the efficiency of the conversion of disorganized forms of energy to organized forms of energy? I hope I didn't mess your minds up, okay? And that's what I'm trying to show you now in a few moments. First, we start by recognizing that the physical laws are symmetrical with respect to the arrow of time. What do I mean by arrow of time? Say, for instance, or consider for a moment a pendulum, as it's shown here. So you have the pendulum, in, well, there's no friction, okay, so it's going to stay forever in this cycle, okay, there's no friction. And this cycle, you can represent it in this graph here, okay, so you have, in this axis here, you have the speed, let's say, phi dot, and here the angular position of the pendulum, okay? And the mechanical law that represents the second law of Newton's second law is written here. It's a differential equation. M stands for the mass of the pendulum. K, yeah, K is actually, this is not exactly, it's K times sinus of theta, okay? So K represents the restitution force, which is gravity, is proportional to gravity, okay? Gravity. And D is dissipation, okay, which is 0 in this case. But the point is that, let me just erase all this stuff because it's going to be polluted. The point is, what do I mean by when I say that the laws are symmetrical? In this situation, if we try to generate this graph here, or the movement, the angular position of the pendulum, theta, okay, we can start at t equals 0 and start to integrate this equation. Okay, so we start here, and we are able to reproduce this trajectory here. Okay, if we invert time, if we consider that time is flowing backwards, it's exactly the same thing. The movement is not going to change. So if we invert time, okay, now it's spinning in the counterclockwise sense. We're going to start from the right, start integrating to the left, because time is flowing backwards now. And what we see is that our law, this t here, this which stands for time, is flowing backwards. But the law, the mathematical equation, does not change. So that's what I say, that all physical laws are symmetrical with respect to time. Okay? Except one. Except the second law of thermodynamics. And this is related to that efficiency that I was talking about. Okay? So what is the second law of thermodynamics? First of all, there are several ways of formulating the second law of thermodynamics. I'm going to give you one type of formulation which is not, which is very useful for conceptual reasoning, but it's not very useful for instance, engineering calculations. Okay, but it's very simple to understand. You just follow me. Okay, so the second law of thermodynamics is related to the spontaneous sense of natural transformations, like the flow of energy. So, in other words, the flow of energy is a kind of transformation. We know that heat flows naturally, spontaneously, from high temperature to low temperature. You don't need to do nothing, okay? This is going to happen without any interference. So when you have a thermal source at high temperature and that someone to receive this energy, we call that a heat sink. Okay, so you can see that there is a natural spontaneous flow of energy. Okay, what we do when we want to convert this flow of thermal energy into some kind of organized form of energy, we need to do this. We need to build some kind of machine, some kind of thermodynamic cycle. Like, for instance, this Stirling engine here has a piston, a double action piston, and have a a working substance inside, which is air, actually. So this, by this mechanism here and the corresponding working substance inside, I'm representing all its complexities in this water mill here. So we're going to use this heat flow, which is, as I said, spontaneous and natural and so on. We're going to tap some of this energy, and we're going to convert that to organized form of energy. Work, like force times displacement, or torque times the angular rotation, okay, that we're going to extract from our heat flow, okay. And the point is, what we want to show is that it's impossible not to reject some amount of heat, okay. Well, since we need to do calculations, we have to state some terms here. So the temperature of the heat source is going to be TQ. The temperature of the heat sink, the heat absorber, is going to be TF. Okay. The amount of heat obtained from the heat source is QQ. Okay. And the amount of heat rejected to the environment or to the heat absorber is QF, and the surplus exergy, okay, is W, leaking in Portuguese. Sorry, I didn't have time to translate absolutely all of my slides, okay. And the definition of this conversion, we're going to define by eta is equal to the surplus exergy divided by the amount of heat that I drain from the heat source. Okay, this is, think in terms of a power plant. This is the electricity injected in the grid from which we obtain revenues, and this is proportional to the consumption of fuel. Okay, so this is the definition of the cycle efficiency. Okay, so as I said, W leak is the equivalent to the work performed by, in the past, a certain number of horses, and that's why we use the word work, because it replaced this mechanical energy, the surplus mechanical energy here in the numerator, replaces a certain amount of work done by horses or men, even men. Okay, so that's why we use the word work. Okay, and that's why we use as a power unit what we call horsepower. Okay, so this comes from this period here, and the denominator is proportional, as I said, to the cost, proportional to the certain amount of coal used in those very ancient Watts and Newcomen's and Thomas Savery's machine. Okay, and as I was explaining, the word work and especially the unit horsepower actually is a concept developed by Watt in order to facilitate his sales. Okay, he was a very clever guy and a very good scientist actually. And well, he wanted to sell his machines to these coal miners owners, and the problem from the perspective of the person who's going to buy, what he needs to know is what kind of machine or what size of machine do I need to replace, I don't know, 700 horses which I have in my coal mine. Okay, so there needed to be a certain type of equivalence between an animal, horse, and a unit of power. So Watt developed the concept of horsepower, which is useful in terms of calculating how much horses can be replaced with this machine model, or if I need to replace more horses, I get a bigger machine model. and also the cost is proportional to the consumption, to the fuel, to the operation cost. Okay, so the search for better efficiency, which, as I said, was very, very poor before Watt, with Thomas Savery and Newcomen's machine. Okay, so the search for better efficiency is related to the use of fuel, which is related to cost, to operating cost. Okay, and also an observation: James Watt became very rich. In addition to being a very, very good technician, he was a very good salesman, actually. Okay, so as I was saying, the quest for maximum efficiency is motivated by, let's say, by greed. You want to produce the biggest amount of horsepower, of surplus exergy, with the minimum amount of fuel. That was, let's say, 200 years or 150 years ago. But today, the quest for maximum efficiency is especially motivated by climate change's concerns. Okay, so we want, actually, what we want to do now is to replace this fossil sources to renewable sources, by renewable sources. Okay, we want to replace that, and we also want to burn the least as possible of fuel, because this has consequences, environmental and social, and so that's another good reason for searching for maximum conversion efficiency. But the problem is, how do I know if my machine is close to this maximum efficiency, or if it's not? Because if it's close to the maximum, to the theoretical maximum, I know that, well, that's nature. I cannot do better than that. Okay, but to know, in order to calculate that, I need to understand how exactly a thermal machine works. Okay, I'm going to explain. So, taking back our reasoning, that's our thermal machine. Inside here, you have a working substance executing a cycle. This working substance absorbs heat from a heat supply. It rejects heat to the environment, let's say, and it exports some amount of exergy. Okay? The heat supply can come from a combustion reaction, as we're going to focus on this class: coal, oil, gas, or biomass. So these are all thermal power plants, but you also can have heat from a nuclear reaction or from the sun. We are going to have a specific class on this subject. Okay, and when we talk about thermal power plants, the heat absorber is always the environment. Okay, it's the atmosphere or some body of water like a river, lake, or sea, but it's always the environment. Okay, and I'm stressing this point because you cannot control the temperature of your heat absorber. You cannot control the heat of the atmosphere, for instance, the temperature of the atmosphere, but you can control the temperature of your heat supply by controlling, for instance, the combustion temperature. Okay, so if you want to produce more more work with less heat, you need to increase efficiency. So a thermal machine, or looking inside the thermal machine, okay, the working fluid that executing a thermodynamic cycle, it can be something like this, like it is shown here. Let's consider, for instance, steam. I have the working substance is steam. Okay, so what do you need to do? You need to get cold water. To get cold water here, sorry, cold water. It's going to absorb heat from the combustion, so you're going to have the cold water is going to be transformed into hot steam. So you have a phase change in between, okay? So if I have a cold liquid, which is heated in your heat supplier, in this case a boiler, okay? And then you extract that in a turbine, and then you can reject the amount of heat that has to be rejected in a cooling tower, for instance, okay? So in this case, you have a pump in order to increase pressure. In the pump, you increase pressure, but not the temperature. So you have cold water here at high pressure, okay? In 3, you have high pressure water and also high temperature water that is that has been transformed to steam, okay? After the turbine, you have low pressure water, still possibly in the form of steam or a mixture of steam and liquid. So low pressure, but still high temperature, okay? So in order to cool down this low pressure water, high temperature water, you have to reject some amount of heat here, okay? And that's related to the maximum efficiency. Just to show you some of these equipments, here are some sugarcane boilers. Actually, these are 2 sugarcane boilers from Bevap sugar mill in Minas Gerais, okay, near Nova Brasilândia de Minas, which is in the northwestern part of Minas Gerais. Actually, there are 2 boilers. You have one of the conveyor belts feeding sugarcane bagasse here. Here is the furnace, and all this is the equipment for removing particles and so on in order to retain all that you cannot emit to the atmosphere. Okay, the turbine is like you can think of it when you if you're not used with this kind of equipment, you can think of in terms of a windmill. So a turbine is a kind of a windmill for steam. Okay, so it's going to remove some of the kinetic energy of the steam, but also some of the thermal energy of the steam. Okay, a windmill only removes the kinetic energy of the wind. So it's a kind of a windmill for steam. The element that rejects heat to the environment can be cooling towers, as in this power plant. So you have hot water in contact with the atmosphere, so it's going to reject heat. It's also going to evaporate. So what this smoke that you see here is not smoke, is steam. Okay, well, so those are the main elements, and the pumps are very small pieces of equipment, so it's not worthwhile showing it to you. Okay, so let me elaborate on the second law of thermodynamics. I'm going to present you what we call the Clausius statement of the second law of thermodynamics, and also the Kelvin Planck's statement of the second law of thermodynamics. These formulations of the second law actually says what is possible and what is impossible. So that's very interesting because it's not quantitatively that you're going to use this formulation of the second law, but it's very rich in terms of interpretation. Okay, so let's see Clausius' statement of the second law of thermodynamics. What he says is that heat flowing from a low temperature reservoir to a high temperature reservoir, it's not possible to obtain this flow without the expense of some amount of work, some amount of exergy. This means that heat's not going to flow from a low temperature environment to a high temperature environment spontaneously. You have to force that some way, by some means. Okay, it's exactly what possibly My air conditioning here is not working, so it's very hot inside, but I suppose you are very comfortable in rooms with good air conditioning systems. So your air conditioning is pumping heat from your rooms, wherever you are, and at low temperature. Let's say that you are at, I don't know, 25 degrees. Okay, so the air conditioning is absorbing heat from the rooms, okay, and is rejecting this amount of energy to the environment, to the external environment, which is at a higher temperature, let's say 30 degrees. Here in São Carlos now, around 30 degrees, okay? So what Clausius says is this is not spontaneous, so it's impossible to obtain that without the expense of some work, okay? So as I said, if you want to produce this flow from a low temperature to a high temperature sink, you are going to have to expend some amount of work, okay? That's exactly what happens with your air conditioning equipment. Let's see, this is more or less natural for all of us because we have experience with this kind of stuff, okay? So this does not surprise anybody. Usually it does not surprise anybody, okay? The other formulation of the second law is less intuitive, okay? So, but it's completely equivalent. I'm going to prove you that, okay? So what says the Kelvin Planck's formulation of the second law of thermodynamics? Well, it says that it is possible to have to obtain work from heat flowing from a high temperature reservoir to a low temperature reservoir. So it says that it is possible. This is natural. This is okay. This does not violate any physical law. But it says that this is impossible. Okay? It is impossible to convert 100% of the heat absorbed from the heat source to work. You have to reject some amount of heat here. Okay? It's impossible to have zero rejection down here. Okay? So let's see. And this is a lot less intuitive. Many times I teach that in undergraduate course. When I show this and ask to the students, do you think this is natural? They ask themselves, well, why this is not possible? Okay, it should be possible. Okay, it should be possible, but I'm going to show you it's only wishful thinking. Okay, so I'm going to prove you that if we accept one of the statements of the second law, the other statement will result from this exception. Okay, so let's see. Let's suppose that this is possible. Okay, let's suppose that Kelvin Planck is wrong, they are wrong, and this is actually possible. So this is our working hypothesis. Okay, if this is possible, to have a machine that produces work only by absorbing heat without rejecting heat, okay, if this is possible, I can use this surplus exergy to drive a thermal machine like this. So I'm going to use this surplus to drive an air conditioning system. Okay, so I don't have to to get electricity from the plug. Okay, I use the exergy from this possible by hypothesis machine. Okay. Okay, so if we assemble both machines and in a single machine, if we consider a single machine, what we see is that we have a net effect which we know is not possible. The net effect is heat flowing from the low temperature reservoir to the high temperature reservoir, because the work produced cancels the work consumed by my air conditioning system. Okay, so I have a net effect of heat flowing from the low temperature reservoir to the high temperature reservoir. Okay, and we know this is not possible. Okay, so by assuming that Planck's machine is possible, by assuming that Planck's impossible machine is possible, we get an absurdity. Okay, so this is proof by reducing to an absurdity. So that means that our hypothesis is wrong and this is impossible. Okay, I hope you managed to follow. So let's come back to the problem of searching for maximum conversion efficiencies. Okay, and this is related to the Battle of Waterloo, or the Napoleonic Wars. Okay, in particularly the Battle of Waterloo, where the Duke of Wellington defeated Napoleon. Okay, in 1815. You know, I mentioned that Sadi Carnot was a cadet at the military school, and Carnot was a very clever guy, actually, and he recognized that one of the main reasons for the British victory was that, well, their guns were better, their cannons were better, or in the whole, their industry was better. So Carnot decided to try to defeat the British in the future, in a foreseeable future, by developing better machines. Okay, so that's really what motivated Carnot. Okay, and he tried to quantify and to state to quantify the second law of thermodynamics, to state to formulate means of calculating this maximum conversion efficiency. Okay, because from the two statements from Kelvin Planck's and Clausius statements, we know that we have to reject some amount of heat. So we know that, let me draw something here. We know that my efficiency, which is equal to W divided by the amount of heat absorbed from the heat source, and I don't know if you remember what is what, QF and W, and by applying the first law of thermodynamics, okay, I can write this as, okay, so here you have QQ minus QF divided by QQ, okay, and finally you have QF divided by QQ, okay. So if QF is always greater than 0 here, that means that your efficiency will be always smaller than 1. Sorry, not smaller or equal. That's my eraser. So it's going to be always smaller than 1. We know that. That's a consequence of Kelvin Planck's and Clausius' postulates of the second law of thermodynamics, but we need to calculate what is the maximum efficiency. The efficiency is always less or equal to the maximum efficiency, which is always less than 1. Okay? How do I calculate this? That's what Carnot was trying to solve. Okay? So let's go back to Carnot, Leonard Sadi Carnot. Okay, and what he did, he thought about our thermal machine as I was showing you. Okay, and he started by recognizing that you have the system, which is the working substance inside the machine, the air inside the piston, inside here, okay? You also have the environment, okay? What is not the thermal substance is the environment, okay? And he recognized that when you invert the sense of the machine, I don't know if you were able to recognize that I have a thermal machine which exports exergy, but I also can have a kind of an air conditioning which imports exergy, okay? We can call that heat pump, for instance, okay? And he recognized that the maximum efficiency, okay, occurs when the thermal machine is reversible. Okay, so let me go back a few slides. He was thinking about inverting the sense of the machine. Okay, I have a thermal machine here. If I invert the sense, I have a thermal pump here. Okay, and his thought was that if by inverting the sense, the working sense of the machine, the effect is nothing. This is a machine that has a maximum efficiency. This is the actual text inside Carnot's book. Okay, by working in the, as he says, the sens inverse, le résultat ne serait alors que la consommation d'un travail égal à celui produit par le fonctionnement en sens direct. Okay. So the maximum efficiency occurs when the machine is reversible. As he says in French, when you invert the sense of the machine, you have exactly the same thing. Okay, I'm going to show you that. So, what is what we call strict reversibility? Okay, so let's start with a thermal machine. I have two units of heat energy being drawn from the thermal reservoir. Okay, these 2 units of thermal energy are converted to 1 unit of work, and I have to reject 1 unit of heat down here. Okay? Okay, so if I consider if this machine is reversible and I invert the sense of the machine, everything happens exactly the same, but in the opposite sense. I mean, this machine here on the left rejects 1 unit of work. The machine on the right absorbs 1 unit of work. Okay? This one produces 1 unit of work. This one consumes 1 unit of work. And both exchange 2 units of heat with the high temperature thermal reservoir. Okay, so when the machine is reversible, when we invert the sense, all these quantities can be maintained exactly as they are. So when we combine the machines, when we use the thermal machine to drive the air conditioning, the heat pump, okay, all fluxes of heat and work cancel out. Okay, so the effect is you have nothing. Okay, because they are all being canceled. So when this is possible, when this happens, okay, you have a reversible machine which has maximum conversion efficiency. Okay, so that's the conclusion of Carnot. Okay, so summarizing a little bit his conclusion, as I said, the maximum efficiency is always less than 1 for a temperature difference which is finite. Okay. Also, he showed that let's take this one. All reversible machines have the same efficiency. You can have different reversible machines. This is a Stirling machine, which happens to have, which happens to be reversible, theoretically reversible. Carnot's machine, which I'm going to show in the next slide, is also reversible. So they are very different machines, but they have exactly the same theoretical efficiency, okay, conversion efficiency. He also showed that all non-reversible machines have smaller efficiencies. So all irreversible machines are less efficient than any reversible machine. And he also proposed a means of calculating the maximum efficiency, which is the efficiency of the reversible machine. Okay, this formula actually was originally proposed by Carnot, not in this way, something like this. Let me use this area here. The maximum efficiency you calculate as a certain function of the temperature of the cold reservoir divided by a function of the temperature of the hot reservoir. Okay, you know, this function f is a generic function, and actually what we call the absolute temperature scale like Kelvin or Rankine. Kelvin is associated with centigrades, and Rankine is associated with Fahrenheit. Okay, this special absolute temperature scales were constructed so that this function is unitary. Okay, so let me just erase in order to clean my slide. Okay, so if you construct a specific temperature scale, you can calculate your maximum efficiencies. Okay, and an important observation here is that when we think about a thermal power plant, the lower temperature reservoir is always the environment. So as TF is always the environment temperature, okay, and the hot reservoir has a temperature which is controllable, because I can control, for instance, the combustion temperature of my biomass, for instance. Okay, and just to write down a working equation, which we're going to need in a few slides, by recognizing that the hot temperature is equals to the ambient temperature plus a certain step, okay, we can replace that and write down the maximum efficiency obtained by a thermal machine, okay, like this, and we immediately recognize that by increasing delta T, okay, if I make delta T bigger and bigger and bigger equals infinity, for instance, okay, going to infinity, okay, I see that this term here goes to zero, this term here goes to zero, and my reversible machine is going to be 100% efficiency. Okay, but you know, this is not practical because, well, you're never going to attain that. But before that, you don't have materials that will resist very, very high temperatures. Okay, so you have practical, in addition to theoretical problems, you also have practical problems. Okay. So also Carnot proposed a thermal machine that is reversible. Okay, I showed you the Stirling machine, which came a lot later. Okay, proposed by Stirling, but at that time, he proposed a thermal machine, which is not practical, but which is not applicable in practical applications, but it represents a very good reference for us, for our studies, for our comparisons. Okay, so let's see what is the Carnot's pump thermal machine. Okay, so he proposed a reversible thermal machine executing this cycle. First, you have the working fluid here, okay, executing this 4 transformations, okay. So you're going to, let's start by here. You're going to absorb heat from the boiler here, okay. So my working substance is going to absorb heat from the boiler or from the heat source at constant temperature. Okay, so if I make a graph like here, a graph of temperature in terms of entropy or pressure or volume, I can use any pair of properties. There's no problem. But if I use temperature and entropy, okay, so the heat absorption part is isothermal, okay, and the heat rejection part of the cycle is also isothermal. So my working substance is going to reject heat to the heat absorber at constant temperature. Okay, so you have 2 horizontal segments, and between the low pressure and the high pressure, you have different, between low temperature and high temperature, you have to change pressure levels also. Okay, so you have a pump here, you have isentropic compression in a pump, and you produce work in a turbine, isentropic expansion in the turbine. If you're not used with these terms, well, isothermal, I think everybody is familiar with the term, is constant temperature. Isentropic means that there is no, means 2 things. There is no heat exchange. So when you compress the working fluid in the pump, okay, you increase pressure, but you do not exchange heat with the environment. So there is no heat loss, neither heat gain from the environment in this operation, compression, and also in the expansion in the turbine. And it also means that there's no friction, there's no any kind of irreversibility in these transitions, in these transformations. Okay, so the name may seem complicated, but the term may seem complicated, but it's actually very simple. Okay, practical problems associated with the Carnot cycle, because as I said, it's a reversible machine. But it's not practical. It's very good for our analysis, but it's not practical. I want to discuss a little bit this because it leads to the actual practical cycles that we're going to use. Okay, so if you consider, for instance, water as our working fluid, you know, maintaining a temperature constant with gases is impractical. Every time that you absorb heat, if you have a certain amount of gas, it's going to absorb heat, it's going to change temperature. You cannot. Why it's going to change temperature? Because the mean velocity of the particles of the gas is going to increase. Okay, so it's impossible to maintain the temperature constant for gases. So this, if you have a gas, your temperature is always going to increase with the same temperature entropy here for a gas. When you absorb heat, when the gas absorbs heat, it's going to increase the temperature. Okay, it's impossible. So if you want to maintain the temperature constant, you can use a fluid that is changing phase. Okay, water, when it absorbs heat and changes to steam, the temperature is constant. So you solve this with a changing phase fluid, like represented here. Okay, here is the liquid portion, here is the vapor portion. Okay, and so with water you're able, to absorb heat at constant temperature. Okay, no problem. The same thing when you reject heat. You reject heat. Okay, so you're rejecting heat to the environment, and the temperature is kept constant. The problem here is related to erosion of the turbine blades. Okay, so why this is so? Because here you have, in this point, you have a mixture of liquid and vapor. Liquid droplets. Okay, these droplets will impact on the surfaces of the blades, and at very high velocities, such as 150 meters per second, okay, or something like this, 80 meters per second, and it will erode these blades. Okay, so this is a very important practical problem, and also pumping a mixture of gas and liquid is a very low efficient operation, also due to practical problems. Okay, so the end of the story is that the Carnot cycle executed like I'm showing you here is not practical. You could implement Carnot cycle like this. Okay, so you solve the problem of pumping a multi-phase flow or blade erosion. Here you have steam, and here you have only liquid. The problem with this implementation of the Carnot cycle is to have very, very high pressures here, something like 10 to the 5 bar. You know that 4,000 bar, let me just make a drawing here for you to have an idea of how much high is 10 to the 5 bar. If you have let's say a steel plate, like, I don't know, 1 centimeter here, 1 centimeter, and you have a jet water, okay, water at let's say 4,000 bar. 4,000 bar. It cuts it's able, this water jet is capable of cutting this steel plate. Okay, actually this is one way of cutting metals, if it's with very high pressure water jets. Okay, so 10 to the 5 bar is really an impossible pressure, so it's not practical for these reasons. Let me just control the amount of time that I have. Okay, so let's go on. So if we cannot implement the Carnot cycle, what can we do? Well, we're going to do what is possible to be done. And what is possible to be done, if the pressure is too high here, I'm not going to allow this pressure to increase to that level. Okay, so instead of limiting the top part of the cycle by the temperature, as in the Carnot cycle, I'm going to limit it by the maximum allowable pressure in the system. Okay, so the limiting part of the cycle is the maximum allowable pressure, which is related to the width of the tubes, the pipes. Okay, it's related to my engineering parameters. Okay, so this is what we call the Rankine cycle. Okay, it's the lower part is equal to a Carnot cycle, but the upper part is actually executed at a constant pressure. Okay, so the transformations of the Rankine cycle, which is not reversible, by the way. Okay, so the transformations are almost the same. Isentropic compression here in the pump. No isentropic meaning no heat exchange and no friction and any other kind of irreversibilities, okay? So isentropic compression. Instead of isothermal heating, we have isobaric heating. Isobaric means constant pressure, okay? So the fluid, the working fluid is absorbing heat at constant pressure, ISOP, okay? Isentropic expansion at the turbine, that's exactly the same as in the Carnot cycle, and isothermal cooling at the condenser. Okay, this is exactly the same as in the Carnot cycle. So the Rankine cycle is the closest that we can get to the Carnot cycle because of these practical limitations that I mentioned before. Okay, so let's see some applications. Okay, I want to be able to make some calculations with you, and actually we're going to compare the best way of, let's say, exploiting, to transforming, to getting exergy from a thermal source by comparing 3 types of cycle. Okay, actually 4 because we always have the Carnot cycle. Okay, so first we're going to analyze a steam cycle, then a gas cycle, then a combined gas steam cycles. Okay, we're going to make these calculations. First, the scenario. You know, this table is very interesting because it shows the thermal efficiency of old and new and future power plants, what is expected to happen for many different states. Okay, so the thermal efficiency obtained in these power plants. You see that almost 20 years ago, the average efficiency was around, let's say, 30, 32, 35%, something like that. Okay, so as the time passes, this efficiency is increased, and what's estimated for 2100 is something around 50%. Okay, and this is just to show you that this is due to the use of combined gas steam plants. Okay, these plants, 30% or something like that is the usual efficiency of a Rankine, or which is for steam, but also the average efficiency that you get in a gas cycle, a Brighton cycle. It's named Brighton cycle. Okay, and by using combined cycles, we get higher efficiencies, around 60 something. Okay, and I'm going to show you that these efficiencies are very close to the maximum theoretical efficiency. Okay, this is just to keep in mind these numbers, because we're going to compare these or power plants or virtual power plants to these numbers here, to these figures here. So let's start by combined gas steam power plant. Well, let me see. Yeah, I'm going to explain the cycle here. Then I'll show the picture here. Okay, so a combined gas steam cycle, whose efficiency we're going to calculate is around 60%. Okay, it combines a gas cycle with a steam cycle. So let's follow the working fluids. You start by burning some fuel, by getting heat from some heat source, by burning gas, biogas or gasification products, for instance. Okay, so you get heat from some source, and you heat air. Let's consider that we have air here. Okay, just to simplify our calculations. So first you compress air. So you have high pressure. You have high pressure here. Sorry, high pressure here, but still low temperature. Okay. Then you absorb heat in the combustion chamber, and you still have high pressure because the absorption is at constant pressure, and here you have high temperature, high pressure, high temperature. Okay, so this is the maximum amount of energy that your fluid, your working fluid, is carrying. Then you expand the gas in the turbine. You get mechanical work in the shaft here. Okay, the shaft. Let me just draw one thing here. The shaft is the same for everybody here. Okay, so you produce mechanical work, which is in the shaft here. Okay, and so at this point here, you have low pressure because your gas expanded in the turbine, but you still have high temperatures, not as high as at the exit of the combustion chamber, but still very high, something around 400 or 300 degrees. It still carries a lot of thermal energy. Okay, so instead of rejecting that to the atmosphere, to the flue gases, for instance, you can use the heat carried by these combustion products, okay, as a heat source for a steam cycle, as it is shown here. Okay, so you pass these combustion gases through what we call a regenerative boiler, and these gases are going to supply heat to the steam, and they're going to become cooler at the exit here. Okay, so you have hot gases, cool gases, then you can reject that to the atmosphere. These gases, they are still hot, not as hot as here and not as hot as here, but still hotter than the absorbed air at the entrance here. Okay? Okay, so let's follow the steam cycle. You have cold water here, cold liquid water, then you compress, so you have cold liquid water at high pressure, then you absorb heat from the combustion gases, and you have here high pressure, high temperature water in the form of superheated steam. Okay, then you expand in a turbine, you produce work. Okay, then here you have hot water at low pressure, then you reject heat to the environment, and then this completes the cycle. Okay, so in the, well, you have the pump consuming energy, you have the compressor which also consumes energy. The net surplus here is used to drive a generator which produces electricity, which you put in the grid in order to obtain your money, your revenues. Okay, so this is a combined gas steam. This is the diagram, and this is what actually it seems. You have, for instance, gas arriving here. Okay, this is the combustion chamber. You have hot gases here. This is the turbine. You have low pressure, still hot gases. This is the regenerative boiler, which produces steam. Steam is driving the steam turbine here, okay, and the cooling tower is back there. Okay, so you always have this same types of equipment in all power plants. Okay. Okay.
Professor,
Go
I have
ahead.
a question. What is the temperature of superheated steam?
Yeah, we're going to calculate that in a few moments.
Okay.
Okay, but typically here, superheated steam, 300 degrees, 400 degrees. Okay, we're going to calculate that in a few moments. Okay. So our machine, what we're going to do to compare all the possibilities is to compare different types of implementations. Okay, so we're going to state, let's say, a benchmark problem. We have a heat source at a certain temperature. We also have a heat sink at a fixed temperature. So TQ and TF are fixed. Okay? And what we can do in order to increase efficiency, if we want to increase efficiency, since we cannot decrease the environment temperature, we must try to always increase the temperature of the heat source. Okay? Oh, sorry for the Portuguese. So the ambient temperature, we cannot control that, and the higher temperature, the temperature of the heat source, cannot be increased to infinity because you have material limitations or practical limitations. Not only material, for instance, if you increase too much the temperature here at this point, because as I showed, you have interest in increasing the temperature here in order to have higher efficiencies. But if you have temperatures, let's say 2000 degrees here, the nitrogen present in the air is going to start to react, and you're going to obtain nitrogen oxides, which will be exhausted here, which in nitrogen oxides, NOx, are very, very dangerous pollutants. Okay, so you cannot emit that in significant amounts. Okay, so the higher temperature is limited due to several reasons. Material resistance, concerns about pollution, and so on. Okay, so what we're going to do, or in other words, our benchmark problem is going to be something like that. We have a heat source at 1000 degrees and our environment at 25. The problem is, what can I do in order to build a machine with the maximum possible efficiency? Of course, if I build a Carnot machine or a Stirling machine like this one, the efficiency can be calculated like this. So if I could build a Carnot machine, okay, the efficiency could be calculated, the temperature minus the temperature of the lower temperature reservoir divided by the higher temperature reservoir by the temperature of the higher temperature reservoir, okay, in the absolute scale. So 25 plus 273 is to transform Celsius to Kelvin degrees, okay, and when we do all the calculations, we obtain 76.6%. And this is the maximum possible thermodynamic efficiency. Okay, so we know that this is the maximum that we can get from these two temperatures here. Okay, so we're going to make different implementations, a Rankine, a Bright cycle, a combined cycle, and we're going to make all the calculations. Okay, let's first start by a Rankine cycle. Okay, as I showed you, this is the temperature entropy graph for water. We're studying the Rankine cycle as the temperature for the superheated steam is too much for a Rankine cycle. Okay, but just in order to be coherent, in order to be able to compare all these implementations, I'm assuming that we are going to build this machine. Okay, so we start at 25. The pressure is atmospheric pressure. Okay, we start by compressing isentropically to, I'm going to fix the pressure here to a certain pressure. I'm not sure where's the pressure here. Well, it's going to be somewhere because I'm going to show you the calculations. So we compress from 25, from 1 bar to the working pressure at the boiler. Okay, then we absorb heat to 1000 degrees. Okay, I have an observation. This is too much for a Rankine cycle. In practice, this is smaller than 600 or 500 degrees. Okay, then we expand that in the turbine. Okay, and we're going to obtain a mixture of actually. Oh, I don't have the calculation here, but well, we're going to assume that we can have a mixture of water, liquid water droplets and steam. But if you have very, very, very small droplets, this is not going to be a problem for your turbine blades, okay? And this is good for the thermodynamic efficiency. So we're going to allow a certain amount of liquid droplets, but we're going to observe, we're going to verify that this is higher than 90%. I mean, we have more than 90% of steam, okay? Well, this is the qualitative representation of the cycle, okay? And we're going to do the calculations, okay? This is the actual Rankine cycle, okay? Yeah, I fixed 100 bar, okay? And you see that it's very disproportional, okay? 1000 degrees is too high. Before moving further, let me just talk about these calculations, this tool that I'm using, because we're going to do the actual thermodynamic calculations. So in order to obtain all thermodynamic properties of your working substance, you have to have, in the past, the thermodynamic tables in paper, I mean, usually in the end of the books, the thermodynamic books, you have these tables, but you have electronic versions already. So I use this software called RefProp, okay? I'm going to show you it in a few moments. RefProp, what I like about RefProp is you have a student version that you can download and install in your computer. It's very, very useful. And RefProp, you can use, I have it here, I'm going to show you. Yeah. So you can use as a standalone software, but you can also incorporate in an Excel spreadsheet or in a LabVIEW application or in C++ or in Fortran. You can link with a MATLAB application and so on. So in this class, I'm using it as a standalone software. You can do a lot of stuff with it. You can plot diagrams, for instance, the temperature entropy diagram for water, okay? You can do a lot of things. So when you use one kind of software like this, the first thing is you choose your substance. So let's say pure fluids, you have a lot of different fluids that can work as a working fluid. So we're going to use water, okay? And what we do, for instance, I want to know what is the enthalpy and the entropy of water at 1 bar, 25 degrees. Enter. So you have entropy, and many other thermodynamic properties. I'm not showing all. You can set properties. For instance, properties you can choose internal energy, exergy. I'm not finding exergy. Flow exergy and so on. You can have viscosity, for instance. Okay, and if you calculate specified point, 25 degrees, 1 bar, you have everything that you need. Internal energy, enthalpy, entropy, viscosity, and flow exergy, for instance. Okay, I'm not going to, I'm just showing how I did the calculation, how I obtained the thermodynamic properties. Is very easy. As I said, you can use any of these softwares. You also have free apps for your cell phone. I use one called, what is it called? I don't remember. It's called Steam Properties. It's free for downloading. Okay, so you have, I don't know how many, but a very large number of possibilities, okay? So going back to my slides, where they are, here, okay? So as I said, I used RefProp in order to obtain all thermodynamic properties of all points. The actual thermodynamic cycle in the temperature entropy diagram is shown here in red, just for you to have the idea of how much 1,000 degrees is in terms of inappropriateness for a Rankine cycle. And also another important observation is the compressed liquid part. I'm going back one slide. Usually when I do these drawings, I distort the compressed liquid part in order to be able to show the transformation. What actually happens is that all the lines here are collapsed or more or less collapsed, so you cannot manage to see the points, okay? So the transformation is here from 1 to 2, but they are in this scale indistinguishable. Then you absorb heat, expansion in a turbine, and in this case you still have superheated steam, okay? Then follow me. By entering all the data that we have, 25 1 bar, okay, I obtain the enthalpy and also the entropy. Point 2 is 300. I wrote 300 bar, but well, it's not 300. I wrote 300 bar and the same entropy here. Okay, but if you wish, we can do here. Okay, let's do it together. This is a kind of tutorial class. Okay, so I'm going to calculate specified state points. Okay, so my point 1, if you remember, is 25 degrees, 1 bar. Okay, and I got the enthalpy, which I'm going to need for the calculations, and also the entropy. Point 2 is at the working pressure, which can be 120 bar or 300 bar. Let's say that I'm going to use 300 bar here. So that's the pressure. And the transformation, I don't know if you remember, so we are at the working pressure, 300 bar, and at the same entropy. Okay, this transformation is isentropic, so we are at 300 bar, and the entropy is the same. So I write 0.36720. Enter, and you have all other properties. Okay, then we go up to 300 bar, 1,000 degrees. 1,000 degrees, okay? I got the enthalpy and I got the entropy. Then we expand that in the turbine, 1 bar, and the expansion is isentropic, so the entropy remains the same, 2.2880. Enter, okay? So we have all our properties. The enthalpies, what we need is are the enthalpies here. Okay, I'm going to show that. So, does someone have any doubts about this? Because that's the only only occasion where I'm going to show you this. Okay, the other calculation, I'm just going to show you the results. I'm not going to show you how you can calculate this. Okay. So, sorry. No. My presentation. So here are all calculations. Oh yeah, I made some calculations, 300 bar, to show you an important thing is that my temperature here is limited to 1,000 degrees. So I'm not going beyond this blue line here. I'm not going above this blue line. But if I increase the pressure, I know, because I already did the calculations, that my cycle is going to be more efficient. So if I increase the pressure, if I move this point 3 to the left, I have higher and higher pressures as I I did 300 bar here, and we're going to end up, for instance, here. Ooh, sorry. So what we have here, you don't have phase change, because here in this region you have boiling water actually. Above a certain pressure, above this critical pressure here, you don't have phase change. You have supercritical fluid. Okay, remember that I was talking about supercritical CO2. That's exactly the same thing, only that the pressures are lower and the temperatures are lower, and the advantage is to have better efficiency. Okay, so a supercritical fluid, as I showed you, is a fluid for which the density of the gaseous phase is equal to the density of the liquid phase. Okay, so you start with below the critical isobar. Okay, you have liquid and gas, and they have very different densities. And when you increase the pressure, the densities become closer and closer, gets closer and closer. Then when they become equal, okay, you have a mixture, like an emulsion of liquid and gas. Okay, so that would be a supercritical boiler, and this is the more advanced power plants are starting to use supercritical cycles or transcritical cycles also. Okay, so this is a tendency that you can observe that contributes to the increase in the efficiency, as I showed in the beginning of in that table. Okay. Okay, so let's do the calculation. Let's apply the first law of thermodynamics, because now we got all enthalpies. Let's apply the first law and calculate the efficiency of this cycle. Okay, 100 bar. Let's calculate that. So what we're going to do, we need to calculate these quantities, the amount of work and heat exchanged. Okay, so we start by, I'm going to do this very step by step, okay, in order for you to follow, and then the next implementations of the power cycle, I'm going to be to move a lot faster, okay, because in principle you got all the more important ideas. Okay, so we start from the data that we got all the enthalpies, enthalpy of point 1, 2, 3, and 4, and we're going to apply the first law of thermodynamics for an open system. Remember, I explained to you what's an open system. Okay, so we're going to start by defining the control volume around the turbine, confining the turbine, and we apply the first law for this control volume. So we know that the amount of heat is 0 because it's isentropic. There's no heat exchange between the system and the environment. It is isentropic, but there is work. Okay, so if we apply the first law, we get that the work W34 equals to the enthalpy change. Sorry. Okay, so we have this in terms of specific numbers, H3 and H4. H3 is here, H4 is here, and the next thing is we do that for other systems. So we do that for the pump, the same for the pump. We put our control volume here, we apply the first law, and we get that the work absorbed is delta H. It's always delta H, okay? And for the last, we put the control volume around the boiler, apply the first law. Here there is no work, the work is 0, but the heat absorbed is not 0. Then you get the heat absorbed in specific terms is delta H, okay, the same thing. So what we have to do now, we calculate with this data here, H1, 2, 3, and 4. Okay, and we get these numbers. Okay, the negative sign here means that work is being absorbed by the machine. Okay, positive means that is being exported by the machine. Okay, the same thing for the boiler. The convention is that heat absorbed is positive, heat rejected is negative. Okay, when we substitute these into the formula for the efficiency, we get these numbers and we get 42.5%. Okay? Okay, so that's the efficiency of our Rankine cycle. We're going to do that for different types of cycle in the same reservoirs, heat and hot reservoirs. So now let's try to use only air. Here we use only water. Here we're going to use only air, and we're going to do exactly the same. The difference, it's called a Brighton cycle, but it's exactly, the transformations are exactly the same as of the Rankine cycle, except that there's no phase change, because air at these temperatures does not change phase. Okay, so you have a isentropic compression to the working pressure. Okay, P max is the working pressure. You have heat absorption at constant pressure. Okay, then isentropic expansion to the lower pressure level, which is the atmosphere. Okay, in that we're going to do between 25 and 100 degrees. Okay, well, this is one possible implementation. So we're going to do exactly the same as we did. This is the machine, okay? The compressor, we get air, we compress, then we absorb heat. So here you have high pressure, high temperature air, expansion in the turbine, okay, and then exhaustion. And the atmosphere is recycling your hot gases, is absorbing the heat carried by the hot gases here, so that you have cold gases in the aspiration here. Okay, well, it's exactly the same démarche. Okay, so for the last time, we go to our thermodynamic proper calculator. We choose the substance. Air is a pseudo pure fluid. Okay, and we calculate the point. So 25 degrees, 1 bar, okay? Then the working pressure can be 20 bar, the same entropy, and so on and so forth, okay? 3.8843, and etc., etc., okay? The same thing. So I did that for air. I got these enthalpies. H1, H2, H3, and H4. Okay. I don't remember, somebody asked me about the temperature here. In this case, we got 300 degrees, 303 degrees. Okay, so you see that it's not as hot as 1000 degrees, but it's still very hot. Okay, so it carries a lot of energy that is being rejected to the atmosphere. Okay, so the idea of combining a gas with a steam cycle is to somehow recover a certain amount of this energy here. Okay, so let's complete the calculations for the Brighton cycle. It's the same story. We put control volumes in the compressor, combustion, and turbine. We calculate the works, the turbine work, the compressor work, and the absorbed heat, and we replace in the calculation formula, and we get 56.18%. And this efficiency we must compare with Rankine that we have just obtained, 42.5. It's better, but it's still significantly below the Carnot's efficiency, 76.6. Okay. Okay. So now, this is just to show you the actual Brighton cycle, and you see that the temperature is very, very high. And you can observe that because you don't see that in a thermal power plant, but you can observe that in jet planes. It's very hot here, the gas combustion. Okay, now what we're going to do now, we're going to analyze a combined cycle. We're going to combine, we're going to try to recover some of this thermal energy using it to drive a Rankine cycle. Okay, so the idea is to combine, as I said, a gas cycle. The hot gases at the exhaust of the turbine will be cooled down by the steam in the Rankine cycle. Okay, so you have, let's follow the diagram here. You have cold water here, low pressure. Then you compress with a pump. Okay, you pump your water. You have, in this point here, you have high pressure, low temperature. Okay, so water is heated in the regenerative boiler. So you have here at point 3, you have high pressure, high temperature water in the form of steam, actually. Then the steam is expanded in the turbine. So here in 4, you have low pressure and some temperature. Liquid water with some temperature, around 100 degrees. The remaining heat is rejected in a condenser. Okay, and the source of heat for transforming liquid water to steam comes from the exhaust gas. So it's the same. You inject, you get air, you compress, so you have high pressure and not so high temperatures. Then you absorb heat. You have very high temperatures and low high pressure. Expansion in the turbine. Here you have low pressure and still very hot gases. Okay, so that's the idea. And in terms of the thermodynamic cycle, you see the Brayton cycle here. So in point 8, the idea is to build a heat exchanger that will get some amount of this heat and inject that to the water cycle, to the Rankine cycle. So our Rankine cycle is built here between the maximum, the Rankine's maximum temperature actually corresponds, is equal to the temperature of the exhaust gases. Okay, so the temperature at 8 is equal to the temperature of 3. The temperature of the gas here is equal to the temperature of water here. Just one observation, this actually is an approximation. When you have actual heat exchanger, even if the temperature, if the area of the heat exchanger goes to infinity, this is not possible because of the differences in heat capacities. Okay, I'm going to show you this. We're going to make some calculations in a future class, but today it's sufficient that we assume this simplification. Okay, because the difference is not very significant. Our calculations for the purposes of today's class is okay. Okay, so the temperature in 3 is equal to the temperature in 8, and the same thing. Okay, yeah, okay. And the temperature in 1 is equal to the temperature in 5. Okay, so now the heat exchanger, the heat exchange between the gas and the steam is in this region, and the point is that the amount of heat that's going to be rejected, it's not from 8 to 5, but from 9 to 5. Okay, so you reject a lot less heat because you are able to exploit some amount of this heat. Okay, so the calculations are here. As I said, I'm not going to elaborate on that. The only observation is that we assume that T8 is equal to T3. So when we do the calculation, we have to set this temperature from air Now we had to inject this temperature here, okay? And as I'm going to show in a future class, we have to make some actual calculations in order to take into account the differences in heat capacities, okay? Okay, so the same procedure. Yeah, well, there's one step before we're able to calculate the efficiency, the overall efficiency of the cycle. We must calculate the relation between the mass flow rates of the gas and of the water, of the both working fluids. Okay, we can do that by applying the first law to the regenerator here. Okay, so the heat exchanged in the regenerator, okay, is equal to the delta H of the gas. That's the mass flow rate of the gas times the enthalpy variation of the gas. Okay, this is equal to the mass flow rate of the steam times the delta H of the steam. Okay, so when we rearrange this expression, we obtain the relation between the mass flow rates in terms of the variations in the enthalpies. Okay, and these enthalpies, all the enthalpies, we were able to calculate a priori. Okay, so moving further, our efficiency is the amount of heat absorbed from the source, okay, the external source, okay, times the net quantities, the total net quantities of work, okay. So in the gas cycle is W78 minus the work produced in the turbine, subtracted the work consumed in the compressor, and likewise this is the work produced in the turbine, and W12 is the work consumed by the pump. Okay, so when we write these works and heat absorption in terms of enthalpies, as we did in the previous cycles, we there's one step that I skipped. Dividing by the gas flow rate, you get this mv divided by mg, okay, which we just calculated here. Okay, so when we replace all the enthalpies that we get, okay, and by replacing the mass flow relations here, we get this final expression, which we can calculate because we know all the enthalpies. Okay, so making all the calculations, the relation, the mass flow relation in terms of kilograms of steam divided by kilograms of air is 0.071, and by replacing all the enthalpies we get 62.5%. That's the overall thermodynamic efficiency of the combined gas steam cycle, combined Brayton-Rankine cycle. So when we compare all our cycles, let's start by the Carnot cycle. We have 76. That's the maximum possible efficiency. Okay, the Brayton got 56, which is good, but not as good as 76%. Rankine was the worst because actually 1000 degrees is too much for a Rankine cycle. And our gas steam cycle attained 62.5%, which is fairly close to the maximum theoretical efficiency of the Carnot cycle. Okay, with the additional advantage that well, the Rankine cycle is sometimes it's used because in addition, sometimes you use Rankine cycle even if its efficiency is not as high as we would expect. You use a Rankine cycle because you also need the heat rejected by the Rankine cycle. For instance, in a sugarcane mill, you use this rejected heat, this heat here, okay, in order to heat water, for instance, for your mills or for your diffuser or for ethanol, for separating ethanol from the wine. Okay, so you need energy in the form of heat, and you can obtain that from a Rankine cycle, but also from the combined gas cycle. That's cogeneration. Okay, so yeah, that's it. You see that I'm going back a lot of slides just to remind you the first efficiencies that I showed you here. Remember, in 2100, it is expected to attain efficiencies between 60 and 70%. Okay, and what we get between 60 and 70%. Let me go to that last slide here. Yeah, okay, so 76 is the maximum theoretical efficiency. We got 62. That's fairly good, okay? Actually, if we can do better than that, I'm going to leave you a suggestion. If you are interested in playing with these equations, what you can do, for instance, here, well, not here, here, sorry. You could try to change your cycle, because, you know, Rankine cycle, it's terrible for that, for 1000 degrees. So you could try to change your Brayton cycle, for instance, by instead of compressing from the lower pressure directly to the higher pressure, okay, oops, sorry, directly to here, I don't remember, 100 bar, for instance, you could compress to a lower pressure, for instance, from 1 bar to, sorry, from 1 bar to, let's say, 50 bar or 20 bar to a pressure lower than the maximum. You can then, sorry, let me erase that. Then you absorb heat. Let's make that. Then you absorb heat to attain 1000 degrees, and then you reject. I don't know if you can see, but you have a different cycle here. You have a different cycle, which can be more efficient than the one that I just calculated. Okay, so that's a suggestion that I leave with you. And there is actually a specific pressure here which produces maximum efficiency. Okay, I'm just going to state like this. I'm going to propose that you study to go after the information, and then in the next class I can elaborate on this. Okay, I can show you what could be this pressure. Actually, the relation between the lower and the higher pressure. Okay, so my point is that you can, even though we obtained a fairly good efficiency for the combined cycle, you still can improve this number by trying to adapt the cycles, both cycles, the gas cycle and the steam cycle, because you observe that I arbitrated some parameters, and you can do differently in order to increase this efficiency, knowing that you cannot exceed 76.6%. Okay, so let me see. Yeah, I'm right on time. If there's no doubts, okay, anybody wants to ask a question? Okay, so next week we're going to focus on more specifics. I'm going to show you a gas power plant and a biomass power plant. Try to analyze the differences, to make some calculations, with this theoretical framework that I just gave you today. Okay? Okay, so if there's no doubt, okay, so thank you very much for listening and for not sleeping. Okay, see you next week.
Thank you.
Thank you, and see you next week.
So,